Okay, so hi everyone. Welcome to our weekly seminar. Sorry for the delay. We had whatever issue today, but now we can finally start. We have with us our very own Grigoris. So let me introduce briefly Grigoris Maravelias. So Grigoris graduated from the School of Applied Mathematics and Physical Science of the National Technical University of Athens in 2004. After completing the master at the University of Crete in 2007, then he worked as a laser technician at the Foundation for Research and Technology Hellas Force. Then in 2010, he received a fellowship from the State Scholarship Foundation of Greece, which enabled him to pursue a PhD in astrophysics at the University of Crete that he completed in 2014. Then he held several postdoctoral positions. First, he moved at the Astronomical Institute of the Czech Academy of Science for 2 years. Then from there to a warmer place in the Universidad de Valparaíso in Chile in 2017. And then finally, he came back at the University of Crete in fourth for a 2-year postdoc. Then from September 2018 to August 2024, he was employed at the National Observatory of Athens, contributing to the ASSES project. And since then, he has been pursuing an alternative pathway with Periastro, while maintaining his scientific collaboration with the Institute of Astrophysics. So thanks for being with us. And
thank you, Carolina, for the introduction. It's a great pleasure to be here to what I believe is my home institute. After so many years in different places, I do believe that this is my home, to be honest. So what I came here to talk to you about is about constructing the largest catalog of massive stars in nearby galaxies. So this is a work that has been done during the ASSES project with a number of people were involved in the ASSES project, plus these names, Paolo and Konstantinos Koplakas, who have been also here. So the idea is, first of all, to discuss about massive stars, and I hope that this will work. Yes, it worked. So this is a stellar evolution in a nutshell. So we start from the very, very small stars, brown dwarfs, which don't change much, right? They will be brown dwarfs almost forever, right? Then we start with red dwarfs. They live a lot, quite a lot, and they end up as white dwarf. Then we have the sunlight, where things are getting a bit more interesting. They become red giants and something like planet and nebula. And then we have actually the more interesting stuff, right? From 8 solar masses and above, we have all the interesting stuff going on with respect to stellar astrophysics. Am I biased? Of course, I'm biased. So why do we bother for these massive stars? First of all, they are driving the nucleosynthesis. Like most of the elements are actually produced at the core of these stars. Then, through the mixing, the supernova remnants, these elements these stars enrich the environments, and they do not only affect the immediate circumstellar environment, but they even affect the host galaxies, right? And not only that, the mechanical pressure input by these stars actually trigger star formation events. Moreover, they are if we talk about binaries, and the majority of massive stars are in binaries, during their evolution, we end up with cases like high mass extreme binaries. We have compact objects, so they are driving, and they are great probes in order to understand high extreme astrophysics, like extreme pressures, extreme temperatures. And of course, they are progenitors of the gravitational wave events. If we consider there are very luminous objects, we can see them at distances much further in the universe, which help us to use them as a tool in order to understand stellar evolution at cosmological times. And with the presence of JWST, it becomes even more important because massive stars, especially very high massive stars, like 1,000 solar masses, which we have not observed, are theoretical expectations so far. We think that these kind of stars existed like in the early galaxies, in the early universe, the first galaxies. So get information from the current massive stars, we can actually try to extrapolate in reality what could be happening in the very early universe. So another very important detail, they are really rare. As much says here, for each 20 solar mass star in the Milky Way, we have about 100,000 solar type stars. And for every 100 solar star, we have about 1 million solar type stars. So they're extremely, extremely rare. And I will show you numbers next. On the other hand, we have also a zoo of massive stars. We have many different types of what we call massive stars. At the beginning, they start like main sequence of objects have 8, 20 solar mass, from above 8 solar mass, and as they evolve, they can become what is known as blue supergiants, or the brachythian supergiants, and not go into so much in the detail of what is what. So this imagine that they are supergiants that are blue because they are on the blue part. These are sources that have a thick torus around them, or rings of material. Then they come red supergiants, they pass through yellow supergiants, red supergiants. These blue, yellow, red comes mainly from which part on the HR diagram they belong to. This is on the hotter phase, this is around 10 to 6,000–7,000 K, and this is below 5,000 K temperature. And then we have extreme yellow hypergiants, which are stars that have dusty environments, and this is one way. And then we have other kind of stars, very massive stars that may have extreme or very strong or extreme stellar winds. They get the envelope stripped, and some of them may have hydrogen, or as this is double band stars, or they may totally lose the hydrogen, and then you do see only the core, the helium core of the stars, the Grigoris stars or lower mass helium stars. And also LBVs, which are luminous stars, which give a tremendous outburst of activity. So this is not in order to introduce you fully in what massive stars are. It's just to show you the complexity that we have many, many different phases, and we have a zoo which has resulted because of phenomenology, because people were seeing different things when they're doing observation. They were calling them different names, and now we try to put all these things into the same, to find the piece of the puzzle and put it all together in order to have the bigger picture. Now, I understand that this is complex, so please give me a moment to get the drive between these two. So, what we saw, what are the factors that affect stellar evolution? First of all, we saw that mass is critical. Don't see the details. See that every starting point here gives you a different track. These are evolution tracks. How the star will evolve according to what we know from current stellar theories, right? So mass is very critical. Then metallicity. Do not look at specific evolutionary pattern. Just look at the pattern. You see that the line changes. The line changes. What it means that if you go from SMC metallicity to LMC metallicity, yes, things change. So metallicity affects, plays a role. And this is important because stellar winds are driven by iron, which is the main element that drives the line-driven the stellar winds. And if you have lower metallicity, you have less iron, so the wind is less efficient. Then you have stellar rotation. Stellar rotation also plays a critical role because as the star keeps the initial angular momentum, you have the initial mixing being enhanced, and this makes the star more compact. And that actually can prolong the main sequence of the star. This is not easy to see, and you have to compare orange to red lines. For example, you can see that the orange does something different with respect to the red line. So we see that in a qualitative way. Binarity plays an important role because you have interactions. So you have two objects and one is gaining material from the other. So this alters a lot the evolution. Take a look, for example, these the blue and the cyan evolution paths. You can see that the blue are the single, and if you put another star, then the evolution path changes totally. It's totally different. So it's a very critical factor. Last but not least, we have mass loss. Mass loss also depends, is very important factor that affects the evolution of a star. Why? Because it helps to remove more or less material from the star. Now, this is an overview of what is the mass loss, what we know regarding mass loss at various phases in massive stars. This is back from a review in like 10 years ago. So what you have here, you have the line-driven winds, which is around this area. This is how they behave, also with they scale with luminosity. This is the Yaher prescription. The 1/3 and 1/10 is just ways to implement this recipe. Some people use 1/3 or 1/10 in order to lower mass loss, depending on what they're doing. You have LBV winds, you have other supergiant stars, yellow hypergiants, and then you have the extreme eruptions by LBV. I don't want you, of course, to remember any of these things. Just keep in mind that there's a huge range of mass loss, and there are a lot of work on the rest. Now, if we try to focus things in red supergiants only, there is kind of a mess, right? In the sense that there are different prescriptions that give you different mass loss results. In this case, for example, Kostas Antoniadis has collected about 2,200 red supergiants in the LMC, and he have derived the mass loss. And this is the bulk of his fitting. And if you try to follow this, then you can imagine that this goes like this. If you compare this with other prescriptions, you see difference. And this is why, because first, people are using different samples. Second, people are using different assumptions. There are many, many unknowns, and people are trying to work with different things. And at the end of the day, we do not have a strict recipe that works for everything. So things are uncertain. And keep in mind that I'm talking about mass loss. What I mean about mass loss, I mean the steady state way of the stars that are losing material. So imagine that on top of that, you can have episodic mass loss. What is episodic? A sudden outburst activity of a star for whatever reason. We know, we have a speculation of what some of the mechanisms are at play, but we do not have a good understanding. Or you have the binary. Again, in a binary, when you have a binary passing through or close to another star, you have material extracted. This is not a steady state of. It may be happening in every orbit, but it is more of an episodic. It's an increase, an abrupt increase in the mass loss. Of course, supernova is another episode of mass loss. Of course, in this case, if it is indeed a supernova, then you have the destruction of the star, and it is one case event. But we have seen also imposters, in the sense that we have seen supernova outbursts like a supernova-like outburst, but then the star survives and gives you and continues giving outbursts. Do we have evidence of episodic mass loss? Yes, because if we look in infrared, we can see that we can find structures around the stars like cells or bipolar nebula and stuff, which is an indication that material has been expelled, dust has formed, and then you have this emission in infrared. We have also seen disks and rings in Plaquetine stars, and one of the most latest events was this great dimming event from Betelgeuse in 2019. What we think happened is that because of the convective cells inside the star, one of them was so huge that actually created a plume that was expelled from the atmosphere. Then as it went away, it cooled down, it created dust, and if you see that in the line of sight, then you have dusty thing in front of Betelgeuse, and that created a dimming. So, episodic mass loss is important, but we do lack the samples of stars with no spectral types in order to investigate how important it is. So, In order to assess that, right, we create the assessing was started back in 2018. It ended up in 2024, and the main question was to investigate what is the role of episodic mass loss, what is the frequency, how it depends on the metallicity, and do all phases of massive stars have outbursts, and how are these linked? So we had a very good track of results. You can see a number of papers in different sort of topics, although they are interconnected. You can see also some pictures of the team, how they evolved from the beginning. Frank, you know this guy, Arkisti, Ming, Stefan, and with time we had people joining the team, PhD students, Stefan, yes, I said Stefan, Kostas, Evangelia, Gonzalo, and then Manos, who you know because he came also in Crete, and this is one of the last photos where we have been joined by Stella working on some benchmarking of the classifier on M31 specifically. So what I'm going to describe here is actually what we did with respect to with the classifier, how we start to develop, how we managed to develop a classifier in order to predict classifications for stars that we don't have any. So we start by constructing our data set from infrared. Why? As I said before, infrared is a very good indicator of mass loss because we can see dust formation, the result of the dust formation, and also because it is a very convenient place where we can separate different populations. For example, the supergiants are gathering up here, or the brachythian supergiants are more off to this plot. So it is a very effective tool. What we did, first of all, in order to build a classifier, you need to have a training sample. At least in this case, we went on with supervised machine learning. So where you need the training sample. We started from mid-infrared catalogs as basis. These are catalogs derived from point sources specifically. Right. Then we combine this with cross-match with optical photometry from pan stars. Then we use Gaia in order to identify foreground stars, and this has been. And then we try to collect what all spectral types known from literature for these 5 galaxies. Now, if you take a look at the numbers, you see that about 1,000 sources are known for M31 and M33, which is the basis of the training. And these 3 galaxies serve as the test galaxies in order to understand how the classifier performs. All in all, we end up with these numbers. They are lower than the numbers you see in the pictures because we had to perform a feature selection. So from Spitzer, we have these 5 bands, 3.6 for 5, etc. And from Pansas, we have 5 filters, right? However, we cannot use all of them. We actually dismissed the 3 largest wavelengths from Spitzer because most of the sources have upper limits, so it was really tricky to use them. On the other hand, we reject G because for 2 reasons. It had issues with faint objects, and it is mostly affected by extinction, which is something that we do not correct for. Lastly, we didn't use Gaia photometry because for the majority of the stars, because we're looking at nearby galaxies up to 5 megaparsec, Gaia doesn't provide any photometry. It's only a small sample. And also at the beginning, we were using DR2, so it was more limited data set. So what we did is that we experiment with various different combinations of these bands in order to create color indices. Why that? Because the color index actually removes the distance dependence. So it is easier to handle in a similar way sources from different galaxies. What we did is that we grouped, and we'll talk in the next slide how we group different objects in certain classes, and you can see the mean value of this feature space from all these classes, and this is the final plot where you see the means from all the different classes. So class selection. If we write down all the spectral types available, you end up with a huge list of about 35 spectral classifications. That's a really hard problem to deal, especially with such low number of sources. It cannot work. So what we decide is we are going to group this in some coarser classes. What we name as blue supergiants, everything that was about O to A, ultra-get stars, LBV stars, B bracket T stars, yellow supergiants, F to G, and whatever is mentioned in the literature as yellow supergiant, the red supergiants, and AGN galaxies. So this class serves as an outlier because you may have a point-like source, which is a background galaxy, and this is mixed with what we try to identify. So again, even after this process, you still see that there are specific classes that have way too low numbers, like LBV6, 17. How to deal with them? We want to keep them because although rare, if you find a few LBVs, that's important. So we'd like to be able, even at the expenses of having a false positives, to include this class. So what we did is that since there is a class imbalance, we try to correct for that. And in order to do that, there are various approaches. One way is to just take the mean of all the features that we have and plug them there. Just to take a random selection of the minority class that we have and do it in a repeated way. However, this doesn't take advantage of you don't sample the feature space efficiently. So we went on to use SMOD. SMOD is a technique in order to perform an oversampling. What it does, it picks randomly a point in the feature space of a minority class. Then it finds a few neighbors around it. So all these are minority class points. It picks randomly one, and then it selects a random point within this, right? And it does that repeatedly as many times as you want. At the same time, also, it is advised to perform an undersampling of the majority class. What does this mean? That you have the minority class, let's say in a feature space like this, and then you have pairs of objects at the very end, at the boundary, where things are getting more complex, exactly because you cannot draw a line around this issue. So what undersampling does, it finds these pairs, and then it removes the majority points from these pairs, but keeping the minority points. What it does, it actually clears a bit the boundary here, so it makes for the algorithm easier to work, right? So,
most of the time, this lane that you throw this data set is narrow or wide.
so what?
I can see that the lane that is withdrawn is kind of narrow.
It depends on your selection. For example, this does what is called Tomelings. It's the pairs of objects that are closer at the boundary between a minority and a majority class. However, you can be more aggressive, and this is what we do actually. And we actually use a nearest neighbor approach, where we didn't find only one, but we have find the three nearest majority points around each single minority. Then we move all of them. So it depends on how you want to do, how aggressive or how strict you want to be.
Isn't this dangerous because it reduces the variance of the majority class?
Yes, but if your majority class is 10 times bigger than the minorities,
So the point is that it doesn't reduce the sample size, it affects the variance of the class. So it affects the shape of the distribution
at the border.
Majority class at the border. And if there is significant mixing between the two classes, and this is intrinsic of the two classes, you're going to miss that.
You're going to miss with the boundary, you mean? Or
yeah, because you have two classes that are mixed, that are intrinsically mixed. Okay, it's not just because you have a lot of points in the majority class. So the two classes are intrinsically mixed. When you selectively remove the majority points on the interface, then you truncate the distribution of the majority point, of the majority class.
Possibly, I have to think about this a bit.
Okay, we can discuss about that.
Yeah, yeah. I will need some time in order to.
I think that this is dangerous. We can discuss about that.
Okay, okay, yeah. Good. So, by doing this, what we must do is, of course, to sample our minority class into the same, to increase the class of minority samples into close to what is the majority and have equally balanced samples. So after doing that, then the next thing is to feed this data into machine learning algorithms. So what we pick is a support vector classifier, random forest classifier, and a multi-layer perceptron. What they do, each of them is a different technique. SVM tries to find a pattern in a high-dimensional feature. Random forest tries to take some sample of the whole sample and some sample of the features and try to find the best ways to split the data. And the multi-layer perceptron is something that tries to do a hierarchical linear mapping of the input to data to the classes. That's a very broad description. However, is there a way to choose any of them specifically? A priori, no, because we don't know. So what we choose to do is to combine in what is called an ensemble approach. In that sense, we took advantage. Each of these classifiers returns a probability distribution. Each class has a probability, and then we actually combine the probability by the same weight, and we end up with this kind of distributions for different classes. So in this case, you see a successful classification, Redspetzai classified as a Redspetzai. You see that the probability is about 82%, very clearly different from the rest. And in this case, you have an LPV classified as Ufraget. The probability is more, something like 33%, and you can see that although LPV of Ufraget is it's classified in Ufraget, the LPV classification is not really that far. So just keep that in mind because I will come to that when I will discuss some selection cuts. At the end, what you do, you actually get one of these confusion matrices that try to tell you how well you predict its class. Ideally, you want to be along this line and you have close to one, right? This is the ideal situation. This is not true for various reasons. The best fraction is close to Redspetzai, and you get pretty good results for people. T-stars, quite okay for blue Spetzaians, the yellow Spetzaians, and results that are not that good for Ufraget stars. And you see that the mixing is that because Ufraget are very confused with LBBs, for example, because if you look at the HR diagram, these classes are not really distinct. There are not strict borders between these classes. You notice that this is one, so you say, excellent, we return, we get all LBBs. Yeah, in this case, it did, but this is just one implementation of the support vector classifier. So in reality, what we do, I mean, it's one split into training and test and the application of the test. In reality, what we do is we do a 5-cross validation approach in order to take advantage of all data. So this percentage drops significantly. And over that, we do that 5 times in order to take the average final prediction accuracies. And this is the result from the different algorithms and the combined one. And you see that overall we get something like 83% individually in different classes. Yes, I'm sure that you're going to pinpoint of this, which is 0. Indeed, there is no much information derived from these two. Something might be derived from support vector classifier. Would you question the results? I agree. But on the other hand, we believe that it's highly important, even if you get some false positives in this case, to go and check them because LBBs are there. So it is important to get them, even if it's not very accurate. Okay, we've done that for the training test. We see that. How well do we do? Because the point is to test in an independent sample, right? So we take the sextans WLMRC 1613, we put the classification, we put the sources, we apply the algorithm, and then we get something like 70% overall. This is just the samples. You see that more or less you get all the superdesigns correctly, most of the blue superdesigns correctly, pretty much working good. Why do we get less than 83%? Well, now that's a good question because we don't know exactly how metallicity affects the classifier, the intrinsic colors of these distributions, and at the end how the classifier performs. Because the metallicity between M31 and 53 is way different than the other three galaxies. I mean, these two are solar or super solar, and while the other are less than solar. Okay, so very well. Now let's go to another challenge point. So quiz time. What do you notice in this image? Time to drink. What is the most obvious thing that you notice? So, I was looking at you.
Missing data.
Exactly. So the point is that we have missing data. Each of the algorithms that I was describing before, they need some kind of value in order to work with this. But in reality, we do have a lot of, this is the test sample on sextans A. We have sources that do not have data. How do we deal with that? So one approach is to say, okay, we miss the data, take the mean of all this, plug it in, and whatever comes out. Yeah, but it doesn't work for stars, right? Because, it's not going to work that well. So we actually, missing values, and the comment that this is not exemption. Actually, what we did is actually we use this multivariate imputation by chain equation, mice. So what it does, really quick, because there's no so much time. First thing first. First of all, the algorithm flags the points where you have missing values. You know that this entry has a missing value, this entry has a missing value. Then it takes the mean or median, doesn't really matter, flags in one initial value, right? Then it considers, it tries to fit using all non-fitted lines across this feature and the rest of the data, it tries to fit them with a linear regression, right? It returns a coefficient with some uncertainty, right? And then given this posterior probability, it samples one coefficient, put this back on the linear regression, predicts the values, right? And it gives some error from the variance of the posterior distribution. It does that for this feature, including all the rest. Then it has a value. It goes to the next. It does the same by considering all other values. This, when it finishes one iteration. And then it does that for multiple iterations, and at some point, this values changes and converts to some imputed values, as we say. It's a bit more complex, but I try to give it as fast as possible.
Your data set has many outliers, and you run this regression. Do you expect that? What I want to say is that you have to apply this algorithm after cleaning your data set.
Yes.
Because if you do it
Yes.
This is
a data set that has been cleaned, keeping only the best candidates, only the ones that don't have any problematic values, the ones that have been cleared from foreground contamination. Yes, it's a clean data. Else, you are driven by the data. I mean, if you have many outliers, then you're going to get another outlier, actually.
There was something relevant to that. So you do the linear interpolation locally around the location, the multivariate location of the point, or globally using all the data.
Globally.
So
excluding all the entries.
So the question is, this assumes that the distribution of the points in this multiparametric space is a plane, because this is the only case where a linear interpolation will work. If you have a hyperplane, anything that cannot be described by linear relation, it will be driven by, we take effectively the mean of all the different parameters.
Mhm.
So, did you consider doing a KD instead?
No,
Like a
at that-
multidimensional KD and
Yes.
sample from the KD?
yes. No, at that moment at least, I didn't think of
Okay.
this. So, I understand there can be drawbacks on this, like what you say, but yes, I didn't do that. So, yeah, that would be, I mean, when I look, this started in 2018, and since then I have gained a lot of
Yeah, right.
experience. And many things will be done in a different way, right? So, yeah.
No, it's
That's-
just funny because if you look at the multi-parameter space, probably it's not a plane, it's something a lot more complicated.
Yeah.
So a linear interpolation may give you a slightly biased result.
Okay, I'll keep that in mind. Okay, so this was the only case we could we could address missing values. So, but we noticed when applying the algorithm is that we make a test and we replace with the mean values, which is prevalent. We see that in some iterations, if we just remove two features, the difference between the accuracy of the test set, we have a test set which has all values. And from this test, we start randomly replacing some of these values with a mean or the imputed values. And we see that if you use the means, then you get something like 30% difference. But if you start using the imputer, you will get something like less than or close to 10%. And if you try to do that with all features, you see that the imputer is quite stable up to 2 missing features, which means 3 bands because we have the color indices. And then it drops after 3. That means 4 bands missing, and then actually we don't have the data report, right? So, given that important detail, we went on to apply the classifier, right? So this was done on a huge data set where we are talking about 26 galaxies up to 5 megaparsec with metallicity range between 0.1 approximately to 1.4. And this is the list of the galaxy, and the final source catalog consists of 1,100,000 sources. So, if you remember from previously, we said the classifier doesn't work if you have too many missing features, because in reality, when we have the catalog, when we construct the catalog, we don't have photometry for all these sources. So we have two scenarios. We're thinking of two scenarios. One was to accept up to 2 missing features, where we know that the drop of loss is about the drop of performance about 10%, and the minimum combined probability above 66%. How this comes up if we take a look of the probability distribution of the correct classifications and incorrect. This is the mean value of the correct classifications, close to 86. This is the mean value of the incorrect classifications. So if we would like to be very, very strict and confident, we could actually select all sources that have a probability larger than 86. But as you can imagine, this will limit a lot the sample size. So what we try to do is go with the mean value of incorrect classifications plus 3 sigma, which is about 0.66. So this is a kind of robust sample. There is an alternative scenario where we can go up to 4 missing bands, have 3 missing features, and a mean probability of 0.5. But this may add a lot of sources, and probably it will add a lot of noise also. So we avoid that. So having selected this, then we run the classifier, and this is the end result about the robust classifications. You can see individually per galaxy and per class, and I have to say that this is the most important numbers. Have about 270,000 sources with robust classification. It's about 25 or 1/4 of the whole sample. And from this, we have about 120 robust classifications for red supergiants, and the rest of the classes follow. So, how good are really these what we predict them to be? So let's make the first test, which is just to plot the syncing, right? You see this, the syncing for M33. We try to plot blue, you would expect them to see them on the blue part, right? Yellow in the middle, red on the right. So more or less, this is what we see. Of course, there are problems, right? First of all, you can see some points up here. Most probably there are foreground sources that we didn't have the Gaia data to correct for all of them. And then you may have some mixing. See a lot of flagged stars. This is not really the case. This is misclassified the sources. But again, looking at the bulk of the CMDs, we see that more or less they are doing pretty much good. You see how well the different stars are separated from the rest of the population in this plot. Okay, how do we assess the performance of the classifier? We have the predictions. So what do? We need known sources, sources with known spectrotypes, and compare the results, right? So we did a huge work on this in order to collect everything possible from the literature. That means about 5,200 sources which have been spectroscopically confirmed. We limit ourselves to this because it's the most secure way to derive a spectrotype, not depending on the photometry or the variability or anything like this. This is from 83 papers. Of course, we look many more in order to, these are 83 cited papers, right? And among these, we also added some of other interesting point sources that we found, like carbon stars, background galaxies, H2 regions, because we wanted to check how well the classifier may actually behave in these cases. Unfortunately, we didn't have any data for these 5 galaxies, and this catalog actually serves as the most complete source for reference currently for massive stars and candidates in the literature.
But since you need no data for these 6 galaxies?
There were no spectroscopically known sources.
Any kind of massive star sources or
Yes.
any other? Just massive stars?
Massive stars. I mean, I wouldn't put only, I mean, if we find the carbon stars only for 52, 53, we would add them, but they were not. To the best of our knowledge.
The reason I'm asking you because 2 out of the 6 are the ones I used for looking for SNRs. And this is, so you just look for massive star spectroscopical data.
Yes.
Not only H2 region for background galaxies or other stuff.
Whenever we were, I mean, H2 regions that look like point sources. I mean, there were papers that were referring to H2 regions and they had the huge catalogs with much larger areas. We didn't include this because they didn't look like point sources. Whenever they would say that they were closer, there were a source that couldn't resolve it, that would be consistent with H2 region, we include them. Does this answer your question?
In other words, so if I give you my spectroscopic data for 2 out of 6 galaxies for the SNRs, would it be convenient to you? Would it give you more info about your sources?
It can help, perhaps, if there is something. Yes, it can help. But if it is, if there are extended sources,
No, point track.
if they are point like this, yes.
So you kind of excluded.
I didn't exclude them, perhaps that we didn't find them. We didn't find the papers. I don't know. What I mean is that we tried to do a little search in order to combine everything that we could find. Now, if we miss the paper, it might just happen like this.
Yeah, the other reason I'm asking is because, okay, first of all, the H2 regions that you are looking at, or probably the spectrum arenas you're looking at, are not the massive stars that you are looking for, right? Because we are talking about different eras.
I'm not interested in specific on the nature. I'm looking, yes, to compare the catalogs and see if this is consistent with a supernova arena, then that could be an indication of that this star is a massive star. But it may happen that in some cases these sources are point sources in Spitzen. We don't know a priori if they are massive stars or not. Many of them could be HB, for example. And they are. Okay. But what I'm saying is that this catalog is clear. This catalog is massive stars only. Our catalog with 1 million sources does contain also other sources, right? Which are misclassified. So, again, this is also something that we did. I need to hurry up a bit. So, in order to assess the performance, as I said, we had to check to match the prediction with the spectral type from the literature. So, in most cases, we did that in two ways. Either there is a direct match, like a red supergiant matching a K, M, or a type or a source with a spectral type of red supergiant. So this is a direct match. But there were cases, as I showed you, where you have a distribution of classes. In that sense, we try to account for this error. So if you remember previously, it was an LBV, which was classified as WR, as Wuffraget. But still, the Wuffraget and the LBV classification probability they were not that far apart. So we consider this and we derive an error estimate on the spectral type. So in order to take this also in account. At the end, and also we limit ourselves into matches within 1 arcsecond in order to between our positions and the literature positions. And if you do all this, then you end up with this plot. So this is success rate with distance and metallicity. What I'm writing above is that when we try to do that, then you have one realization. When you try to compare the success rate that you do in a galaxy based on, let's say, 5 sources out of 15 sources, this is one manifestation of the binomial distribution. In order to properly correct for the errors, we did the Bayesian approach where we derive the likelihood based on the binomial distribution and the prior, which is a uniform prior in this case, or a unimodal beta distribution based on the results of the classifier from paper 1, which is the method. All in all, what I'm going to say is that we try to properly treat the errors because if you put a symmetric error here, this will end up below 0, which is unphysical, right? What we are looking at the end is that the classifier performs quite well with distance. Of course, there is a drop after 3 megaparsec. You see that the performance drops a bit. Why? When you go further away, confusion is getting larger. So you may end up confusing your source with the neighbor. You may have another source within the same aperture, for example, in Spitzer photometry. So confusion plays a role. But if you look at the metallicity, then we see something interesting, that we see that more or less things are quite equally distributed across the metallicity. So the classifier is actually performing quite well even at lower metallicities. Metallicity to 0.6. What do you mean with metallicity? No, this is metallicity. The metallicity here, we strive to get metallicities which come from massive stars as much as possible. So we measure massive stars, the metallicity derived from fitting spectra of massive stars in order to get the metallicities. In most cases, not in all galaxies, because this was not doable in all of them. Okay, good. Now, another thing that we would like to examine is how this opulent. Now, what we saw now previously is the total performance of the classifier across all classes, right? So we would like to explore now how each class performs with how the predictions of the classifier at each class performs with metallicity. Not performs, actually investigate now how the metallicity affects the population of each class. But before doing that, we need to consider some caveats, which are kind of important, because there are some completeness issues. First of all, we are using Spitzer as our base catalog. What does this mean? That we are looking at infrared bright sources. But this is not valid for all cases. We have many OB stars which are not bright in infrared, so you are missing population, for example, in this case. And we had the opportunity do that for 600 series, while Lorenzo et al. Managed to uncover almost the whole population of OB stars there. And if we compare the two catalogs, we get an overlap of 30% almost. So indeed, we are losing most of the population. Then there's a galaxy inclination. If you have a galaxy face on, you can actually, or if it is a low mass galaxy, you can, not low mass, if it is a diffuse galaxy, you can see most of the population. But if it is an edge on, a fraction of the population is covered behind the galaxy, right? And also galaxy type and star formation. It's not the same thing if you're looking at a galaxy that recently produced stars, while with a galaxy that had a star formation like 5 million years ago, right? Some of your stars like Wolf-Rayet will have died already. Then there are some observational limits. Spitzer has limited properties, right? What we discovered is that, for example, when looking at NCC55, we were able to derive 2 out of 4 LBVs. But the other 2 were not recovered, not because our approach was bad or the classifier didn't perform well. It was just because they were not in the database. Right? Because the points were such that these 2 regions were not covered. And last, unfortunately, there's no photometry for many sources. Like, we cannot derive robust classification for 75% of the sample. Given all this, with a grain of salt, for example, we end up to these plots. What do they describe? They describe the blue supergiant population across metallicity, the big brachytelial stars across metallicity, etc. So what we want to see now is how these populations behave. If we take a look at, let's start from the easy ones, LBVs, not many samples, of course. We don't have any, we cannot draw any robust conclusion. The idea is that at least you see that there might be sources even at low metallicity, and this is something that we actually observe. Now, with big brachytelial stars, similarly, this is another rare class. It seems that there is, the distribution is flat, right? There's no indication of a trend here. But yet, you do see that there are stars in low metallicity environments, right? So this is not actually known. We do have a paper that showed the first big brachytelial stars in low metallicity environments. But again, we do not have any idea of how this population, how we can get to this population. There are no models that can predict this population. So it is interesting to see that still they survive even in low metallicity environments, right? And then what do we have? Then we have Wolf-Rayet stars. So this is quite okay with what we expect, in the sense that we do expect a drop of the trend as we go to low metallicity. Why? Because we said that Wolf-Rayet stars are stars which have really strong winds, stellar winds, and these are driven because of the metallicity. So as you drop the metallicity, these are becoming less and less efficient. So it is normal to expect that this is going to be the trend that you see. Now, let's move back. We have blue supergiants, right? And yellow supergiants have more or less similar behavior. It seems to they are getting, as you go to lower metallicities, it seems that the trend is going upwards. This is also kind of expected, because as you go to lower metallicity, the angular momentum of the star is retained more. Then you have internal mixing. Then you have more compact cores of the stars, and this prolongs the main sequence. So you have more and more sources staying, or having more time as yellow and blue supergiants than getting faster at the red supergiants. So it seems that it is quite okay with what we think. And keep in mind that this has to do with the blue supergiant and yellow supergiants that do show dust, right? And last but not least, red supergiants. What do you notice here? So I would say that if we draw a line, it seems like you have an increase of the population as you go to lower metallicity. Actually, this is not expected, in the sense that what studies show so far, red supergiant mass loss is not really depending on the metallicity. So in reality, what we would expect, more or less, a horizontal trend, a flat trend. Why this is happening? We believe that this is an observational bias in the sense that as we go to galaxies with lower metallicity, then the majority of the population is on blue and yellow supergiants. We have less red supergiants, and overall, if you take this number over the total infrared sample, then you get an increase in fraction, right? Because you're actually missing most of the population. Yes, and last but not least, I have 2 slides more to finish. So we kind of pinpoint some interesting cases. We have some extreme red supergiants in this sample that challenge actually the Humphreys-Davison limit. What is this limit? This is an empirical limit defined by this dust line, where you don't see any, for example, red supergiants above these 5.80s luminosity. And newer studies place this a bit lower at 5.5. Why? Most probably because at this region, the atmospheres are stable and the stars cannot sustain cannot be sustained. But if we put these luminosity functions, we actually find quite a few sources that are above this 5.5, and actually 6 of them have are more than 6, not 5.5, but 6. So 6 with log larger than 6. And actually, these are indeed M31 members. Why I'm saying that is that we may find 22 plus 28, 30 sources, but not all of them have Gaia data. So probably most of them could be foreground sources. We are not sure. So we cannot really claim anything. But for 6 of them that we do have Gaia data, and we believe that really M31 members, we have an indication of very high luminosity, which challenge the Humphrey-Davison limit of this. But this is a very good opportunity to give actually it's a very good case for follow-up studies on this. What is it? Humphrey-Davison. Yes.
What is that?
What is it? It is an empirical limit. You don't. It is a line drawn here in this. It's a diagram above which generally you do not see stars. It's an empty space. You may have, on the other hand, you may have LBVs getting into this region, but during an outburst, but then they return. So it is a kind of instability region that stars do not pass much of the time.
It's only empirical there.
It's mostly empirical. Yeah, the idea is that you have instabilities, but it's not a concrete theory behind that yet.
And it is luminosity against effective
Temperature.
temperature.
And last, we also found out some about 160 interesting sources. These are called yellow hypergiants. Why they are interesting? Because if you plot this 3.6 to 4.5 infrared color, this seems to be these are the whole yellow supergiant population. This is the cut based on the mean value and the standard deviation. This is consistent with what we typically find in yellow supergiants. And if you take all sources above that, these are considered yellow supergiants which have really a lot of dust around this. This is highly indicative of stars that probably lost a lot of mass during the red supergiant phase, and they actually went into the blue loop and they became yellow before perhaps progressing and becoming blue stars. So this population is important in order to understand the connection between the yellow supergiant and the red supergiants, and actually it is a link to the red supergiant problem. The red supergiant problem is what is called the deficit of supernova eruptions of red supergiants going supernova. Because if you have a red supergiant going supernova, you will see some hydrogen because the hydrogen is still there. But if you remove most of the envelope, then this is lost, and then you get more of supernova that do without hydrogen. And then, yes, this is my summary. What we did is that we developed a massive classifier We applied it to a huge data set with key outputs, providing classification for 1.1 sources. About a quarter of this is robust classification. So I understand that the question can be why claim about this when you don't have robust classification, but you still have an indication of something, so they can be used for follow-up observations. We have about 120K research results, which actually has been the main topic of the ASSESS project. We have actually identified observation and worked with a lot with red science. We also provide the largest spectroscopic profile catalog of massive stars. So we believe that this is a power tool for follow-up studies as a source catalog and observations, especially with ZWST, which would be quite sensitive in infrared and can resolve a lot of ambiguities regarding these sources. Thanks.
I'm a bit confused in the sense that since there are spectroscopic classifications in the literature, why you don't use them in the initial training?
Because there are few. I mean,
but you already your samples.
Yeah, but you have to have two things. You have to have the spectroscopic data, and you have to have the photometry, the data to train. Not all of them have data to train on.
I mean,
what I want to say is that
having spectra, but not usually you do the opposite. You first have the photometry, and based on the photometry, you take the spectra. But
yeah, but I need the photometry with which I'm working. So I need Banzas photometry, Spitzer photometry. They may not have this combination. They do have photometry, of course, but they don't have necessarily the features that they want in order to achieve. One is this, and keep in mind the following: that this is what we collect from the literature. It's not when you cross-match with the infrared-based catalog that we have. Many of these sources are not included in the infrared catalog. So you end up with much less sources in order to work and train. Most of the training sample comes from M31 and M33, which are the closest and the ones that we have enough samples to work with. Because the rest have 10, 15, okay. Yes, you could combine all this at the end, but you have to keep in mind that when we were doing this, you have to do also collect the classification. So we had to balance a bit how to do. When we wanted to work with the classifier, see if this makes a sense, we have to be faster, not to collect all the literature yet necessarily.
No.
I mean, if we had such a catalog from the beginning, that would be awesome, because we would use the catalog, cross-match with the photometry, and then we have the training sample ready. That would be.
Maybe you can update.
It is true that it can be updated, yes. After, exactly, because many of these works, some of these works they were available after, even after the publication. Right, yes. So, for example, many sources come from our own observations, right? Yes, we can go back now, given these samples, and retrain. We can do that. We generally speaking, like student, any volunteer, perhaps.
Okay, apart of the technical stuff, what is let's say, the most important finding of this work, in the sense that the initial goal was to see how the episodic mass laws related with all the parameters, as you said in the beginning.
Yeah.
So, how the statistics of this application helped on that? What would you say is the most important finding?
For me personally, although it's kind of messy and needs careful attention. I think this is the best result because you're looking at the population with metallicity. And these populations are the ones that are prone to have episodes like Ufragids, like red supergiants, like big Blackheatistas, LBBs. Okay, blue supergiants perhaps not so much. Yellow supergiants, if we consider the yellow hypergiants, yes. But I think this is, for me, this is the most important thing. But in order to derive more robust things, more robust conclusions out of this, we need to carefully start working on this careful selection of this sample. One example, red supergiants. We have collectively assigned the red supergiant class to any object that looks like that. And this can be done, that can be shown easier here, because very similar to red supergiants are RGBs. And RGBs tend to have B here. So you see, actually, these are RGBs, right? But there is not a good way to distinguish between HB and red supergiant. So in order to photometrically, you can put some criteria, but then what are you going to do in this mess? It's not easy. So you need to develop more tools. And actually, what I'm thinking about this plot is it will be a driver, perhaps, to investigate more what's going on. And actually, this is the trend. People are going and checking low metallicity galaxies, you know, to see how different the stars look like them, how the metallicity affects the population and the properties of the stars. So I believe that this is a driver motivation to go back and say, okay, you have a catalog. Let's see how many of these are true, really. I mean, you have a catalog to pick, for example, for follow-up studies. This is extremely very important for these sources, actually. These are 6 sources, right? Or big 20. You can go back and check, are they really foreground sources or not? If they are foreground sources, okay, yes. Humphrey David's limits are close to that. Okay, we are consistent. But if they are not, and they are indeed M31 objects, then this challenge, it's not 5.5 as they say, it's close to 6. Why? This is important. And the dust ones.
Are there any binary populations in this model that predict the number of these different stars as a function of the list, just to see some trends there?
Yeah, there are. I mean, if you look at the very beginning when I saw the BPAS models, for example,
Yes.
which are binary, they do show the evolution. Now, you have to, these are theoretical, so on top of that, you can plot what you observe from photometry. You can actually collect and say, okay, this population has that many numbers or so.
Yeah, I was thinking more about comparison, if your findings align with theoretical.
If you find?
Your findings about how, like, the supergiant would increase, so the populations in this model find the same?
I don't know. We have to ask people how to do the population sequences and evolution in order to verify this or not. I mean, but as I told you about red supergiants, at least we think it's an observation bias, not a real bias. Because currently, especially the work of Kostas, that examines red supergiants across different galaxies, across different metallicities, it shows that more or less the metallicity doesn't play a major role in this, in the mass loss. So you wouldn't expect much difference.
Yeah, but with respect that perhaps mergers or the more higher star that will become forthright, maybe we can represent.
Yes.
That kind.
Yeah, I don't know. This we need to put the evolution models now to see how many sources you predict, how many you observe. But keep in mind here that we cannot distinguish between binaries. So we are looking at a source. If it is a binary, we cannot tell. We just look at the total photometric properties. And actually this is data driven, right? Because you're looking at the data and we train on the features of the data. What you say is now how we can connect this with theory, which is the ultimate, definitely. Because if you have a concrete knowledge and concrete numbers about the populations, then you can go back and test them with evolution theory. Yeah, this is actually what Manos was trying to do with Also by considering the mass loss recipes derived from these works, and go back and check how many sources do we see.